Thanks very much, Chris. Yeah, firstly, it was really good to see the demo here today, and that actually makes it a bit more easier to try and explain some of this sort of stuff. And I guess it helps me, to support with some of the things that we're doing here. Now, we've been, as Chris said, we've been working a fair bit with handball in an indoor sport, which is quite demanding in terms of, obviously, we're indoors, we're in really tight spaces. You can think of this as the game is almost like a small-sided game in football. Not much high-speed running, distances covered, but it's this short, sharp change of directions, really challenging movements. Now, a lot of our work has been with the inertial sensor data, but also with now with ClearSky. And we've got projects, I've got a PhD student and various master's students that have been helping with this data. Now, we have done a fair bit with the S5 units. When we're indoors, obviously we turn off the GPS and we're just focusing on the inertial sensor data. We had actually had the first version of ClearSky when we trialled that, and then we waited until the very compact and great little unit, the T6, came on. And being a scientist, we actually wanted to weigh this in very scientific scales, and it was 28 grams, this little unit's here. So tiny. And you saw Paul took you through in terms of the basic setup here, and James explained a little bit about. There's a few questions about exactly how is this calibrated and how do we do this, and I can actually show you this. And one thing that I really like with this system compared to some of the other LPS systems is that it's the portability and flexibility of the system. So we can have a very portable system, or it can be a permanent setup, or a semi-permanent setup. And I'll show you what I mean here. So we've got a big hall in Oslo where we've got 3 handball courts, and you can see these nodes or tags or receivers or whatever Paul liked to call them, around the edges here. But we never really know which court we're on, so we can actually calibrate all 3 by ourselves. So we can have our nodes hanging up for hall 1, and then the next day we're on hall 2. So we can literally, if we've pre-calibrated, then we can literally just move these nodes and we're ready to go in 10 minutes. So if any clubs are interested to purchase the system, they might have just one permanent setup in their stadium, or maybe they want to have a setup in their stadium and 1 or 2 training venues, an indoor setup and a training pitch outdoor. So the Catapult guys could easily calibrate 2 or 3 locations, mark them up. So as long as you know exactly where each node is and which order it is, then it's relatively a simple process to move them, connect your computer to your timing node, and then you're ready to go. And that's one of the great things I like about the portability and the flexibility, depending on the environment and what sort of stadiums or indoor, outdoor setup you have.
Can I ask a quick question?
Yes.
Are they wireless or are they wired?
In our setup, ours are wireless, so we literally just got our cable to our timing node. Yep. Because we don't need to. It's actually, the setup is quite clean and we don't have too much interference. But that's the flexibility setup. So it really depends on the environment. So we're independent. So we've got a philatellite, so we can actually calibrate ourselves. And the basic process is, we sit up in the centre of the court, zero our angles, and then we focus in on each node. You can see the little laser lighting up here on our reflective marker on our node. And we do that in order for all of our nodes. Once we've done all of them, then we take a marking or reading on each corner of our handball court, and then feed this information into software, and we have basically a calibrated court Now, we've done this in football. We've got projects in football. So you can see here an indoor football stadium here. We've done exactly the same thing here. And here we actually have both teams hooked up with ClearSky devices. Again, so it's the exact same process. So we're self-sufficient, but obviously the Catapult guys, if anyone purchases a system, will actually do this for you. And that's, again, a really simple and neat thing about the system is, the flexibility and portability. And as you saw today, that the animation, you can hook up the data with people running on the lines, and actually you've got your animation here. And one thing is the physical data you can actually get, but it's the animation in terms of drills. So what we do in Handball is, with the national team, sometimes we'll hook up the system and they want to look at particular specific training drills, and the coach will stop it and he might scroll back and just want to say, okay, let's have a look at the defenders. What was the spacing between the defenders? Is this exactly what we want? He can actually check that and go, okay, that's good. So it's not only the physical data we can get, but the animation stuff, I think, is another key part. Now, with the new ClearSky 2 system, once we got our hands on it, then we really wanted to do a really good validation of this. So what we did is we've got our Qualisys motion camera set up here, and what we've did is we've got a calibrated area here, 10 or 12 meters here, and this whole area is calibrated to the accuracy of about 65 millimeters. So in this area, we can set up different specific drills, like short accelerations to decelerations, change of direction, zigzag circuits, etc. And as I mentioned, we've got different halls. We've got Court 1, Court 2, Court 3, and we wanted to look at a few different environments. So Hall 1, we've got most of our work which has been done first, but also we wanted to look at a really tough environment right on the corner here, where in our hall, it's only a couple of meters from the wall to the playing surface here, and a couple of meters to the side of the court. And that's a really tough environment where is unlikely to be tougher in different sports here. So this is really a worst case scenario. So here's our area, where's our calibrated area, and I'll show you some data from here. And we're working on this data here. And one thing I can say is, in a really tough environment, the validation is poorer here. However, again, with the portability and the flexibility, then we can easily just have additional nodes around the court or change the setup to potentially increase the precision here in this tough area. So again, it really depends on your setup and your environment to improve the precision of the measurements here. So I'll show you a little bit of data from this validation study in this area here. What we did is we completed a few different tasks. So this is for basically all team sports, but for specific for handball, here's some short acceleration to a deceleration to a stop. We had sort of a defensive shuffling course, which where they went back and forth 3 times here. Change of direction course here, which is maximal accelerations here, turn, deceleration to a stop. A zigzag court with a zigzag circuit with a pirouette here. And finally, a zigzag maximal effort here where they jog back, and they did this 4 times. Just to sort of really test this out. And again, this is tough environment in compared to most of the games. Obviously, you're looking at straight line, jogging, striding, high-speed running, and this is really the toughest part you'll find in critical play of team sports, basically. So, again, we're set up here. So we've got our unit in a vest. We've got our reflective marker that we're our reference point. And here in this example of actually right in the corner I mentioned, in that really tough environment, which most places wouldn't be as challenging as this. So we've got a trial here. We do a jump to sync the data, change of direction to deceleration to a stop. And here is one example where we've got our reference system, Qualisys, sampling at 1,000 hertz. This is our gold standard. And here we've got ClearSky, so which was, in our data was sampling about 17 hertz. So you can see all these tight circles here, 100 hertz versus 17 hertz here. And if we overlay this for this trial, it's looking really good. And a meter is a meter here. This is calibrated, a calibrated area. Another example here from one of those zigzag circuits which I mentioned. So where they did a zigzag maximal effort here, then they jogged back to the start, and they did that 4 times. And you can actually see the patterns of the path where they've run is very, very similar here. If I show you an example, again, this is 1,000 hertz versus 17 hertz. If we put them together, both sampling at 17 hertz, we've got ClearSky in the red circles, Qualisys, our reference systems, in black. It's virtually overlaid here on these paths. Looks really nice. Now, this is looking at it from another angle. If we're looking at from a forwards direction, so from a starting point to an ending point, here basically overlaid here, they jog back to the start of our circuit, and this is looking from a lateral perspective. So the zigzag lateral perspective, again, we're literally overlaid here. Again, so we're really happy with that. If we're looking at, and this is work on progress, so we actually just got some of this data a day or two ago. And again, here is our 5 different drills you can see here. And we've tried to break this down between the differences between our reference system to ClearSky, and break this down into the differences here in absolute position differences. So this is less than, in meters, so this is less than 5 centimetres, 5 to 10 centimetres, etc. for our different tasks. So as you can see here, for most of the error, for these real challenging short lateral explosive type efforts, most of this error is within about 20 to 30 centimetres here, and occasionally greater than here. One thing to, I guess, point out here is in drill 1 and drill 3, these are very short explosive efforts, short acceleration to deceleration, maximum acceleration to a change of direction and a stop. Whereas this one is a shuffling task where they come from the middle to the back, 3 times. And this is a zigzag circuit. They jog back and do this 3 times. And you can see over a longer duration, our accuracy is better. But again, this is really good for this type of challenging type of tasks. If we look at this in terms of distances here, so again, we've got our 5 different tasks, got our reference systems, so this is our distances covered, and this is ClearSky. Again, looking really nice, and this is what backs up a bit what Chris has just shown from today's demo. And this is the mean differences. So in 14 centimetres here, 60 centimetres, etc., etc. And if we want to look at this as percent differences, we're looking at 0.5% to 1.5% for distance in positional stuff. And I think most people would be very happy with this sort of data. And if you look in this compared to GPS stuff, we're not looking at 0.5% or 1%. We're looking 3, 4, 5% when we're looking at that type of data. So again, happy with that. Very happy. Another way that these types of validation studies have been doing is mean speed, and that says one thing, and I'll talk a little bit more about this later. But again, we've got our 5 tasks here. Our reference system, gold standard versus ClearSky. So remember that task 1 was our acceleration, deceleration to a stop. So we're reaching higher mean speeds here. And task 3 was our maximal acceleration and then a change of direction. So these are a bit greater mean speeds compared to some of these other tasks. But again, we've got our mean differences here in meters per second and our mean differences, so between about 0.5% to 2.5%. And given the very explosive nature of these tasks, again, we'd be very happy with this if you compare that to traditional GPS type of measurements. And another slide which has just come hot off the press, which I received from my PhD student yesterday. Now, here we have, I believe, 32,000 data points. I haven't counted them all up myself, but here we've got our reference speed, our reference speed from our gold standard Qualisys system, and our absolute differences. So this is instantaneous speed for various meters per second. So here, and there's this levers nicely color-coded these for into, for example, from in yellow we've got 1 to 1.5 meters per second here, and for example in blue here we've got 2.5 to 3 meters per second. So this is our reference speed and our absolute differences. And here is the absolute differences on an average, and here is our standard deviation. So this is one thing that a lot of the other studies haven't really looked at, is the instantaneous speed. And this is actually a nice starting point, because then the next point we want to look at is more precise on the acceleration component and versus the deceleration component. So this is, again, I think, really nice thing that we're working on. And again, this is just current work in progress. So hopefully this will be completed in the next month or so. Now, Chris mentioned the importance of the inertial sensor data, and I'll briefly just show a couple of examples from our work with the S5. So when we're in handball, S5s, we're indoors, so we turn off the GPS and we're looking at the inertial sensor data, which these inertial sensors are pretty similar to the inertial sensors from our new ClearSky system. So I'll just give you a couple of examples from our work in international handball games. So this is the Norwegian national team in international games, and I just want to look at a study which is published, where we want to look at the basic differences between back players, wing players and pivot players. And this is our standard player load per minute. So when we're looking at player load per minute, this is a general indication of intensity. And these are data points of individual players in different games. And the white circles here are players that play both in offense and defense, and black are only those who play in offense. So one thing you can basically say here is the general intensity is pretty similar between our outfield players, backs, wings and pivots. But if we then look at high intensity events, which is greater, what we're defining as greater than 2.5 meters per second, then we start to see some interesting things here, where the wings do a lot less high intensity efforts. This is a combination of accelerations, decelerations, changes of directions, compared to our backs and our pivots. So that means that the wings do more free running, moderate intensity type efforts, given the fact that they have a similar play load. Now, if we break the back players into more detail, then we can look at this into the accelerations per minute, decelerations per minute, and changes of directions per minute. So we can see in most of these high intensity events are in a change of direction component. And this is giving us much more detail than what we've traditionally had. And as some of the guys mentioned before, if we tried to do this, if we had GPS indoors here, we wouldn't get to this level of detail at all. And this has been really valuable, because again, this is from international games, and we can use this data in training, which we're doing now. So that's one, again, real value for the inertial sensor data, both for profiling individual players' positions in games, and we can use this data in training. And I'll just to finish up, a couple of slides on reliability. This is another study which we've just had accepted. And what we did, I'll just talk a little bit about the field study. So we had a field study and a lab study. A field study, we had an elite men's handball team in Norway where we just followed 12 training sessions. We got 7 of the key players monitored with 2 S5 units. As you can see, 2 units here strapped together. We had control over which units. We actually fitted this into a mixed model and followed their training, and we looked at their data in terms of the AMA, inertial movement analysis counts, and the play load metrics. And what we can see here is we have device 1 and device 2, and then this is their mean data. So we've got our standard play load, which is our play load 3D, which most of you guys are using the data will be using, play load per minute. Again, this is our measure of our general intensity. And there are probably 2 key metrics that most people are using. If you look at those, with the percent CV, our percent error, 1%, which is fantastic. And this is less than half of what we call the smallest worthwhile difference, or our signal that we want to measure, and the error is less than half that. So we can be extremely confident with that. We like other people, always look at play load 2D, which we omit the vertical acceleration because we get a vertical acceleration every time we run, and it's highly correlated with distances covered. So again, if we do that, the reliability of that is excellent as well. And you can also split this down into the various vectors here: anterior, posterior, medial, lateral, or vertical. And again, our percent error is very good in relation to the signal we want to measure. So we can be extremely confident with play load metrics, and also with IMA counts. Now, there's various ways we can do this, and we use the intensity bands that from the Catapult software, being low, medium, high. And you can see this here, low being 1.5 to 2.5. Then we've got medium, high. Combination of medium and high being greater than 2.5 metres per second, which we're using, or total being greater than 1.5. And here is our raw data in counts from our training sessions. So again, this is 80 pairs of files here, using all types of training drills in handball. And our CV here, when we're looking at total or a combination of medium high, is very good, less than our smallest worthwhile difference, or our signal that we want to measure. And even if we split this down, it can be a little bit variable, but still reasonably good. But you just need to keeping that into mind in terms of how you interpret the data. But again, if you compare this to general GPS data, most GPS reliability types data is around about here, or even greater than 3 or 4, 5, 6%. So again, that's just a quick summary in terms of the inertial sense data. I've got a much more data here, which I haven't been able to present here. But if anyone wants to talk about or ask me a little bit later, then I can talk a bit more about that. So just to sum up, with the ClearSky data from our experience, we're really happy in terms of flexibility and the portability. From our data, with our positional accuracy data, we're really happy with this. This is work in progress. So hopefully we'll be finished with this in the next couple of months. But the combination of the positional locomotive data with the inertial sensor data, I think, is excellent. And if there is if someone has this system, the ClearSky system, and is unable to set up the nodes, then you can always just work off the unit with one timing node, and you can actually just get your IMA data without actually having positional data. So again, the flexibility and portability, I think, is excellent in terms of other competitive LPS type systems.
Thank you, Mark.
Okay, thank you very much.